All right, team, I'm just too psyched to wait to work these out ahead of time, so we're going to do it live. So bear with me. There might be a lot of editing after the fact. So the E&M questions are out. Woohoo! Let's roll through. Okay, so two very long cylindrical current carrying wires. Wires S. Yeah, I know. My toddler's here too, by the way. Are oriented parallel to the y-axis as shown in figure 1. The centers of the wires are in the xy plane and they're described as follows. Wire S has a radius of 2a and is centered at x equals 0, as a non-uniform current density and carries a total current I naught in the positive y direction. The magnitude of the current density in wire S as a function of the radial distance r from the center of the wire is described by J equals CR, where C is a positive constant. Dope. Okay. Wire T has a radius A. Wire T has a radius A and is centered at x equals 10a. Wire T has uniform current density and carries total current I naught in the negative y direction. Okay. Point P is located inside of wire S at position x equals A. So you're at x equals A. Derive an expression for the magnitude of the magnetic field at point P due to only the current in wire S in terms of CA and physical constants as appropriate. Begin your derivation. Dope. So that is going to be Ampere's law. That's an Ampere's law problem. That's an Ampere's law problem. Okay, so if we do kind of like a cross section of that wire, here's our total radius. Our total radius goes out to 2a. We care about at A, so we're going to draw a nice Amperian loop where we want to figure out the field, and that's at point P. Isn't that right? My little mac and cheese monster. Yes. Okay. So Ampere's law says if I integrate around I know. So Ampere's law says we're going to integrate around the closed path of B dot dl, and that's going to be equal to mu naught I enclosed. All right, so I'm going to choose an Amperian loop that is a circle because that means B and dl at any point.
No.
I know. Remember, your magnetic field of current carrying wires makes concentric circles. So B dot dl, that dot product is going to go away because they are parallel at all points. We chose our surface in such a way, I know, in such a way to make that true. So on the left side, B dot dl, B is going to be constant because we're at the same radius this whole time. So it's the current density that's not constant. That's going to come in on the right side. The magnetic field, it doesn't depend on where on the circle I am, just at what radius. So he's going to come out. Then we get our closed integral around that path dl. That path dl is a circle. So remember, the circumference of a circle goes like 2 pi r. And if you're like, IDK, what that goes, integral of dl, there's nothing in there to integrate. dl is just the path. So that's going to be B times 2 pi r. So at this radius, though, we are at radius A. So that's going to simplify to B times 2 pi A. So on the right side, the I enclosed is what's going to be tricksy because we have a non-uniform current density. So we know that our current density goes like constant CR. I'm gonna erase this part just so we don't confuse circumference with that constant C. So current density goes like CR. If you remember, current goes like the integral of J dA or something like that. Pretty sure. Let's double check. But that's actually a dot product. All right, so integral of J dot dA. So J depends on radius, and that's a current density, and dA, we're going to make a bunch of symmetry arguments that current's going down the wire. So that means J is going down the wire, which means that's parallel to our cross-sectional area vector, which is down the wire. So that's going to be the integral of CR. Now dA, that's our cross-sectional area. Remember, if you forget how to get dA, so I know that the cross-sectional area of that is a circle, which goes like pi r squared. So I'm just going to take the derivative of that. So that's going to be 2 pi r dr. So that's what's going to come in here. So that's going to be times 2 pi r dr. And I'm integrating from 0 to the radius I care about, which is going to be 0 to a. Meow, meow. All right, 2 pi is constant.
Yeah.
C is constant. I know. So we're going 0 to a. That leaves me behind an r squared dr inside. We're going to integrate that. That's going to be 2 pi c. Integral of r squared goes like r cubed over 3 from 0 to a, which means that I enclosed is going to be 2 pi c a cubed over 3. And I don't know why I wrote all of that over here, because I need that over here on the right side. So that I enclosed is going to be mu naught times 2 pi c a cubed over 3. Those 2 pi's are going to cancel out. One of them a's is going to cancel out, which means b at that point is going to be mu naught c a squared over 3. Que bonita. Dope. All right, that was a nice softball for your first one. Love that. All right, AII. We want to sketch a graph of the magnitude B of the magnetic field due to the currents in both wires as a function of x along the x-axis in the region 2a to 9a. So in this empty gap in here. Okay, so that means we're going to want to bust out some right-hand rules. So for wire S, my current is going up the page, which means my field is going to make circles into the page in this zone. My field from T, my current's going down, so my field in that zone is also going to be into the page. Okay, cool. So that tells me that those fields are going to end up adding. All right, so that means my B total, that's going to be my B from, what are the names again? S and T. BS plus BT. Okay, luckily for us, they want to do this outside of the wire. So for BS, they actually tell us that the total current is I naught. So outside of the wire, the total current is I naught. So outside of the wire, it behaves just like a regular old wire. So if you remember, you could rederive it. We aren't required to, so I'm not gonna. So you can get Ampere's law the same way. So outside of the wire, the magnetic field of a straight wire goes like mu naught I over 2 pi r. So I'm going to get mu naught I of S, which they actually called I naught, right? Over 2 pi, and then it's going to be X is what they called it instead of R. And then in wire T, it also carries a total current of I naught. Dope. Okay. Plus mu naught I naught over 2 pi. Now the tricksy part here is that we're measuring it from 10A. So for wire S, that distance, let's say we wanted to come here to some R. So the distance from the center of S to that point is just R or X, wherever I'm at. However, for my wire T, if I want to write that in terms of X, it's going to be 10A minus X is how, I don't know why I did that. So that distance from here to here is going to be 10A minus X. So you get that whole 10A minus that little piece. So that's what's going to go down here because it's the distance from the center of the wire. Cool. So if I pull out all of that constant junk, I get mu naught I naught over 2 pi, and then a 1 over X plus a 1 over 10A minus X. Okay, so we're going to get some functional dependence that's like 1 over X plus 1 over 10A minus X. So you notice all of our X values are in terms of A. So like if I'm at X equals 2A, I'm going to get all that constant crap, 1 over 2A plus 1 over 10A minus 2A, so 1 over 8A. So really I end up getting an A on both of these, so I can pull it out. So it's going to end up looking like mu naught I naught over 2 pi A with 1 over your x value plus 1 over 10 minus your x, the number value of your x. So we can hit up Desmos to see what the shape of that graph is going to end up looking like, just to kind of guide our plot. All right, so if I do 1 over x plus 1 over 10 minus x, that is going to be exactly what we kind of expected. So between 2 and 10, well, I guess 9, we're going to have a minimum exactly halfway. So I'm going to make sure I have a minimum exactly halfway on my graph. We can get some numerical values out of there. So, Given that they gave us grid lines, we're probably going to need to be accurate-ish. Except it says sketch, so maybe not. We'll find out. So we're going to have that minimum at 5. So I'm going to put that minimum down here. At 5. It's at a value of 0.4. And over at 9, we're at a value of 1.11. Let's make 3 boxes equal to 1. That sounds fine. So if 3 boxes is equal to 1, 1 box would be 0.33. That'd be like there-ish. At 2, we're at 0.625. So 0.2, so like 0.67 is a little bit less than 2 boxes. We're being really specific. I don't know if you need to be this specific, but it doesn't hurt. Let's do 7. You're at 0.7. Where's 0.5 at? 7.24. Okay. And then we got some nice symmetry going on. Meow. 0.5. So like 2.75. Cool. So like 2.75. Wait, no, we said that was 0.5. So that's like here. And then 7.2 for like here. So it's going to be kind of like wow, 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 wow. Something like that. And since my graph sucks, I'm just going to specify that's a minimum. Just going to specify number without A's. Okay. So that's going to be a minimum. And it's going to be stronger over at 9. Because you're closer to the center of this wire, who has the same current as this wire. So it's going to be stronger over here, less strong over here, minimum in the middle are probably the important parts. Okay, so part B. At the instant shown in figure 3, a small sphere with charge Q is at horizontal position x equals 5a. So that's where we had that minimum. And moving in the xy plane with a speed v in the positive x direction, at this instant, the net magnetic force exerted on the sphere due to the currents in wire S and T has magnitude F. Derive an expression for F in terms of AQ, R naught V, and physical constants as appropriate. Begin your derivation by writing fundamental physics problem. Okay, so we have a charge moving in a magnetic field. So that's our good old F equals QV cross B equation. Lit. We coincidentally already found our B up here. V is perpendicular to B, so that's going to be QVB. Do we need to find the direction too? Or just the magnitude? It doesn't say. Alright, so our charge is Q, our speed is V. That B field we found earlier was mu naught I naught over 2 pi 1 over x plus 1 over 10a minus x. And if you're not sure where that B field came from, go back and watch part A. Okay, so we are specifically at 5a when we have that magnitude of F. So I just have to plug in 5a and I'm good. So I'm going to plug in 5a. So I got 1 over 5a plus 1 over 10a minus 5a, which is 5a. That's the name of our cat. So those 2's are going to cancel out. So the magnitude of that F is going to be Q, V, mu naught, I naught, over 5 pi A. Cool. All right, the end. Dope.